Ever wonder how a single cable can carry so much data all at once? Well, today, we're going to pull back the curtain on the unsung heroes of our digital world. We're talking about the powerful duo that keeps all that information flowing without a single crash: multiplexers and demultiplexers. So, here's our game plan. First, we'll tackle the big problem these little devices solve. Then we'll get to know the multiplexer, or MUX, and its perfect partner, the demultiplexer, or Demux. After that, we'll see how they work together as a team, and we'll wrap up by looking at the incredible impact they have on the technology you use every single day. All right, so before we dive into the nitty-gritty of the circuits, you gotta understand why they even exist. What was the huge challenge that needed a solution like this? Just think about it for a second. We have an unbelievable amount of information flying around the planet. Phone calls, TV shows, all our internet data. How does all of that travel down one single pathway without just becoming a jumbled mess, a total digital traffic jam? That's the core problem we're talking about. You know, the easiest way to picture this is with a highway. Imagine you've got this massive 10-lane highway full of cars, but up ahead, there's a single one-lane tunnel. To avoid total chaos, you need a really good traffic cop to let cars in one by one. And on the other side of the tunnel, you need another cop to direct them all back to their proper lanes. That, right there, is basically what we're doing with data. So, let's meet the first part of this system, the traffic cop at the tunnel's entrance. This is the component that merges all those lanes of data into one. We call it the multiplexer, or MUX for short.
At its heart, a multiplexer is a really smart digital switch. It's looking at a whole bunch of input signals, but it only picks one of them to let through to its single output at any given moment. And because its whole job is to select one piece of data from a crowd, it's often called a data selector. Makes sense, right?
So how does it pick which one to let through? This is where the magic happens. It uses something called select lines. You can think of these as a digital address. By sending a specific binary code to these lines, you're telling the MUX exactly which input to connect to the output. And what's really amazing is how efficient this is. With just 2 select lines, you can control 4 inputs. With 3, you can control 8. The number of inputs it can handle grows exponentially, which is a huge deal for designing complex circuits. Now, to keep all of this straight, engineers use what's called a truth table. Now, don't let the name scare you. It's nothing complicated. It's just a simple instruction manual, a cheat sheet for the circuit. It just lists every possible combination for the select lines and tells you exactly which input gets to go through to the output for each one.
Let's look at a simple 4-to-1 MUX right here. See the 2 select lines, S1 and S0? If we set both of them to 0, the output, which is Y, gets its signal from the input D0. Now if we change that address to 1 and 0, which is just binary for the number 2, boom! The MUX now selects input D2 and sends that to the output. It's a super simple and elegant system.
Okay, so we've neatly merged all our data into a single stream. But what good is that if we can't separate it back out at the destination? Well, for every MUX, there's an equal and opposite partner, the Demux, or Demux.
These two are a perfect pair, really. They're just mirror images of each other. The MUX is a many-into-one device. It takes a bunch of data streams coming in at the same time, in parallel, and lines them up into a single file, a serial stream. So it's a data selector. The Demux does the exact opposite. It's a one-into-many device. It takes that single serial stream and converts it back into multiple parallel streams. It's a data distributor. So a Demux takes one single input line and sends that signal to one of several different output lines. And just like the MUX, it uses those same select lines to figure out where the data is supposed to go. It's kind of like a train conductor who switches the track to send a single train to one of many possible platforms. And you can see this perfectly in its truth table. It has just one data input, D. When the select lines S1 and S0 are both set to 0, the data from D is sent out through output Y0. All the other outputs, they stay off. Now, change the select lines to 0 and 1, and the data gets routed to Y1 instead. It perfectly reverses the MUX's job.
So while these components are pretty useful on their own, it's when they team up that they really unleash their true power, managing this massive flow of data across just one shared channel. Together, they create this incredibly efficient system in just 3 steps. First, at the sending end, the multiplexer combines everything. Second, that single, compact stream travels super efficiently over just one wire or channel. And finally, at the receiving end, the demultiplexer separates it all, making sure every piece of data gets to its correct destination.
So we've been looking at diagrams and tables, but what do these things actually look like in real life?
Well, they're these tiny black chips called integrated circuits, or ICs. These little guys are the physical workhorses inside our gadgets, performing these super high-speed switching operations millions and millions of times every second.
So why does any of this matter to you? Well, because this MUX-DMUX partnership is basically the invisible backbone of all the modern technology we can't live without.
I mean, they are literally everywhere. They're why India's massive mobile network can handle billions of calls over shared fiber optic lines. Inside your computer, they're helping the processor grab data from exactly the right memory address without a mess of wires. They're how organizations like ISRO get huge amounts of data from satellites all the way back to Earth through a single channel. And as we look to the future, they're essential for things like IoT and smart cities.
You know, this quote from our source material really just sums it all up perfectly. This technology isn't just about making things fast, it's about making them efficient. By cutting down the number of wires and simplifying the design, MUX and DMUX are what allow us to build the smaller, cheaper, and more reliable devices that we all depend on. So as we look ahead to an age of 5G, the Internet of Things, and entire smart cities, the amount of data we need to manage is just going to explode. That means the job of these digital traffic cops is only going to get more important. And that leaves us with a pretty interesting question to think about. What new, unimaginable data traffic jams are waiting for us just around the corner? And how is this elegant piece of technology going to help us solve them?